All right, so now let's move on to some examples. So here's example 1. Suppose you draw a card at random from a standard deck of cards. Which of these pairs of events are independent? So remember, you're just drawing one card. Just because they say events, it doesn't mean you're drawing two cards. It just means that it's like two different aspects of that card, like heart and jack, right? So here it says, is getting a heart independent of getting a jack? Does knowing whether you have one affect the probability of the other? So we could write out sort of the rule for independence of events. So probability of heart given jack should equal the probability of hearts, period, overall, right? Is that true? Well, let's think about this. So there's only 4 jacks, so that's my whole universe, and the probability of getting a heart is 1/4. But then so is the probability of getting a heart overall. Ta-da! So I would say these are independent. Now, I chose probability of heart given jack, but you could have also done it the other way around. I'll write it in a different color. Probability of jack given heart, right? Is that equal to the probability that you'll just draw a jack, period, right? Well, the heart world is 13 cards, right? So out of 13, there's only 1 jack, so that's 1 out of 13. And the probability of drawing a jack is 4 out of 52, which is 1 out of 13, right? So eventually we get 1 out of 13. And we see that it doesn't matter which event you pick as your condition, they're independent. Okay, so what is the probability of, so are these two events independent? Getting a heart or getting a red card? Okay, so we could set that up again. Heart versus red card. Heart given red card. And is that the same as the probability of just getting hearts overall? Well, we already know this one. It's 1 out of 4, same as here. Is the probability of getting a heart, given that you already have a red card, going to be different? Well, half of the cards in the deck are red, hearts and diamonds, right? And so that's 26 cards. So out of those 26 cards, half of those are hearts. So 13 out of 26 are hearts, right? And that's really half of those cards are hearts if you know that it's already a red card. So 1/2 does not equal 1/4. So I would say these are not independent. So here, I'd say independent. Here, not independent. And remember, you could always test it the other way as well. Probability of red given heart, does that equal the probability of getting a red card? Okay, what about this last one? The probability of getting a 7 given heart, and is that equal to just the probability of getting a 7? Well, let's see. So the probability of getting a 7 is that there's 4 sevens, 1 for each suite, out of the 52 cards. So 4 out of 52. And that's going to reduce to 1 out of 13. Because it's a rate of 1 out of every 13. Because for every suite, you only have 1 7. Okay, but what about probability of getting a 7 given that it's a heart, right? So if it's a heart card, that's only 13 cards. The probability of getting a 7 is 1 out of 13. Well, these are equal. So I would say independent. Ta-da. Here's example 2. The U.S. Department of Health and Human Services found that 30% of young Americans, 18 to 24 years old, don't have health insurance. If you sampled 2 young Americans at random, what is the probability that the first has insurance and the second doesn't? Now, first, you might think, oh, this is sampling without replacement. And so you might think, that sounds conditional. But actually, if you're sampling from like the entire United States, because it's just 2 young Americans at random, probably the fact that you picked one guy, it changes the probabilities by such a tiny infinitesimal amount that it sort of doesn't matter. So we could treat this as almost independent events. And frequently, that's one way that independence is used, for almost independent events, where it might affect it just slightly, but so little that you would need so many decimal places to even account for that difference that we just sort of ignore it. Okay, so think about drawing one young American. What is the probability that any one young American will not have health insurance? Well, that's 30%. So what is the probability that the drawing one American has health insurance? So here's the first guy, right? Has health insurance. Well, that will be 70%, right? And then you can multiply that by the probability of the second guy having second guy not having health insurance. So that's 0.3 or 30%. And so if you multiply those together, then it's a 21% chance that you will get the combination that the first guy has insurance and the second, no insurance. And remember, we know this because of the new, revised multiplication rule, where we could just look at this as being equal to the probability of the first guy having insurance times the probability that the second guy has no insurance. And that's 21%. Example 3. A state school gets 1,725 applications. Are being admitted and going to private school independent events? Well, that we could apply our definition of independence. So is the probability of being admitted, being admitted given private school, is that equal to the probability of just being admitted, period? Well, let's look. Here's the probability of being admitted given private school. So that's this universe right here, right? And that's going to be 220 over 483. That's my probability of being admitted given that they go to private school. Versus the probability of being admitted at all, right? So this is 870 over, everybody. And we want to know, are these equal to each other? So I'm just going to use Excel as my little calculator. So 220 divided by 483, that gives us about 46% chance of getting in if you go to private school. And 870 over 1725. Ooh, and slightly higher chance given you go to, given slightly higher chance of getting in, all things being equal. This is probably not true, though. Probably you have a better chance of getting in if you go to private school, but I don't know. So that's, 46% does not equal 50%. So I would say, it's small, but there's a slight difference between those, between being admitted and these aren't independent because there is a slight difference in the conditional probability versus just the overall probability. All right, example number 4. About 11% of college freshmen have to take a remedial course in reading. Suppose you take a random sample of 12 college freshmen from around the world, from around the U.S. What is the probability that none of the 12 will have to take remedial reading? What is the probability that at least one will have to take a course in remedial reading? Well, here we could use the multiplication rule, right? Because we could assume almost independence. Picking 12 college students at random, there's so many people, it's almost like sampling with replacement. It's not going to affect the probabilities that much. So what is the probability that the first guy, right, the first kid, does not take remedial reading? And you want to multiply that by the probability that the second kid does not take remedial reading, right? All the way up to the probability that the 12th kid does not have to take remedial reading, right? And that would really just be, so it's not 11%. If you draw a person at random, there's 11% chance that they have to, that this college freshman has to take remedial reading. So the flip side of that, not having to take it, is 89%, right? So that would be 89 times 0.89 times 0.89 times 0.89, 12 times, right? So 0.89 to the power 12. And so that would be 0.89 to the power 12, 24.7%, right? So 0.247, right? So about 25% of students of this sample, like if we took a group of 12 people, 25% of the time, all 12 do not have to take remedial reading. Now, what is the probability that at least one will have to take a course in will have to take a remedial course? Well, we shouldn't apply this rule because we don't know which one of these guys don't have to take. Which one of these guys takes the remedial course, right? We don't care which one. Also, we don't care if it's the first and second, or the first and third, or the first, second, and third, or all of them, except for the last guy doesn't have to take it, right? So, so we just want to know what is the probability that at least one will have to take a remedial course. Well, that's every combination, right? When one person, 2 people, 3 people, 4 people, all the way up to 11, right? The only case we want to leave out is when all 12 do not have to take the remedial course. Well, we just found that. So what we could do is 1 minus the probability that all are exempt. Oops. Exempt from remedial reading. Woohoo, right? And we already know that, right? So it's 1 minus the 0.247, right? And so that should give us 75.753, yeah. That should give us about 75% of students, 75% of the samples of 12 will be samples where at least one where they have to take a remedial reading course. So ta-da! So that's a shortcut. That's like the real way because any other way would be just really insurmountable.